Dr. Christopher Johns-Krull is a chair at Rice University, and it's going to basically talk about Blue Sky Space, a UK space science data company that has just launched its first satellite. Mauve, is that right? Is that how you pronounce it? Mauve, Mauve, yeah. Making the start of a 3-year mission to study the stars and how their activity influences the habitability of distant exoplanets. The satellite was launched on the SpaceX Falcon 9 rocket on November 26th as part of the Transport of 15 rideshare program. And Mauve will enable the study of transients and energetic phenomena from stars, largely emitted through powerful explosions. Stars that go boom, I think people get very excited about that, and known as flares that will affect the planets around them. The emission is largely seen at energetic ultraviolet wavelengths, which Mauve can observe over long periods of time. In addition to stellar flares, research priorities include young exoplanet hosts, hot stars, and binary stars. Dr. Christopher Johns-Krull is professor of physics and astronomy at Rice University and Blue Sky's interim vice president for research. Dr. Johns-Krull researches star formation and early stellar evolution, in addition to solar and stellar magnetic activity, in addition to extrasolar planets. And Dr. Johns-Krull is a key member of the Mauve science program. So really looking forward to this talk. I think it really connects well with a lot of interest from the club. So we're going to take 2 minutes to get set up and switch over, and then we can start with a talk. Yep.
All right. Well, thank you. Thank you for having me. It's a pleasure to be here. I've changed the title of my talk slightly. I'm going to talk about Mauve itself and go over a number of the science programs, and then I'll talk a little bit more specifically about the one that I am basically leading, which is on a class of planet-forming young stars called Herbig B stars. But first, I wanted to tell you a little bit about myself. Thank you for the introduction. What the introduction didn't cover was my pre-Rice history. So I'm originally from Dallas and went to the University of Texas at Austin for my undergraduate degree, and then then out to UC Berkeley for my PhD in astronomy. And then I bounced back and forth between Austin and Berkeley. I went back to Austin as a postdoctoral fellow, formerly at McDonald Observatory. I was appointed at McDonald Observatory, which means you spend most of your time in Austin and you occasionally go out to the observatory to use the telescope. And then I went back to Berkeley as a research scientist for a few years before finally coming to Rice as an assistant professor. But I fell in love with astronomy, I think, in many of the same ways that you all have fallen in love with astronomy. When I was about 9 years old, I saw Saturn through a telescope for the first time. Was at a slumber party of a friend of mine, was having a birthday party, and could see Saturn, could see the Cassini division, could see the rings, and just thought that was the most fascinating thing I'd ever seen. And so from the time I was 9 years old, I knew that I wanted to be an astronomer. That kind of is a little bit ironic because one of my roles at Rice is a divisional advisor, meaning that I advise incoming freshmen. And so, one of the things that we try to tell them is that college offers you a lot of things that you probably never thought about. Don't worry if you don't know what you want to do when you graduate and when you first come in, you will figure it out. And then they ask, well, when did you know what you wanted to do? Well, when I was 9 years old. So, my friend that I first saw Saturn with had a Meade telescope, a Meade reflector, but I couldn't afford a Meade, so I saved up money for a Criterion Dynascope. It was a fantastic telescope, and you were mentioning your dark site. So I grew up in Dallas. I was a member of the Dallas Astronomical Society, and they had a dark site out near Kaufman, Texas. So I spent many a nights out at their dark site with my Dynascope. It was a truly wonderful thing, and it's what got me into astronomy. And I probably still have my Messier certificate somewhere. Not sure I could pull it out real quick, but I probably do still have it. But then I came to Rice in 2001, continuing to do research in astronomy. And so I've graduated a little bit from the little 6-inch telescope. So these are some of the telescopes that I have used and use regularly, including the 2.7 meter out of McDonald Observatory. So I do still regularly observe out of McDonald. Have some projects going on with the Hubble Space Telescope as well. This is the Lick Observatory 3-meter telescope on Mount Hamilton, where I did my thesis research. But there's a fun connection between my sort of professional life and my amateur life between these two telescopes. So if you remember when comet Shoemaker-Levy 9 plowed into Jupiter, the 3-meter Lick, there was a team of infrared astronomers using that to take spectra of the impact sites. And of course, when you are using a telescope at an observatory, you're almost never looking through the telescope, right? It's all connected to the detectors are connected to computers and so forth and so on. So I was living in Berkeley, and unfortunately Berkeley is often foggy because the fog comes in from the Bay Bridge. So we had my roommate and I, apartment mate and I had to go somewhere with my dynoscope to actually see it. So we drove up to the observatory. I set up my little 6-inch telescope outside of the dome of the 3-meter telescope, and everybody in the dome wanted to come out and look through my telescope so they could actually see the impacts with their eyes. So that was a fun little adventure there. As was mentioned, my main area of research is in the area of star and planet formation. And I'll talk a little bit more about that when I get to the part of the Mauve mission that I am most directly associated with. And star and planet formation are intimately bound up because when you form new stars, as far as we can tell, basically every forming star forms with a disk of material around it, which is the raw material out of which planets can form. And we see that process happening. And Mauve will help us understand a little bit of that as well. So Mauve. Mauve is a mission that has been launched, as was said, by Blue Sky Space. This is a UK space technology company. And one of their main ideas is to try and bring relatively low-cost space missions to consortia of people, universities, researchers, and so forth that have the ability to put forward some money. Now they get some money from the UK Science Research Council, but a lot of it is funded by the members of the different consortium. Mauve is the second mission, I believe, that they've launched. They previously launched something called the Twinkle mission. But I will tell you a little bit more about Mauve. So Mauve has a science program. You have to, one of the main motivations to go to space is to get to parts of the spectrum that are not covered from the ground. So even though Mauve does go out to 700 nanometers, so very much into the optical spectrum, its short wavelength range is at 200 nanometers, which is well short of the ultraviolet cutoff of the Earth's atmosphere. So it's primarily a spectroscopic mission. It has a nominal 3-year lifetime, and it was originally conceived as a mission to monitor flare stars. But there's lots of other things you can do with a mission of this type. And so they basically put out an open call and let anybody who wanted to join, as long as you brought some money with you. And then you have the ability to create your own observing program that tries to best use what Mauve can provide. Mauve itself is a small telescope, so it's a 13-centimeter Cassegrain design telescope. So you're primarily looking at pretty bright stars. Its main thing that it allows, though, is approximately 5,000 hours a year of observing time. And we have a relatively small science team, so it's ideally suited for time domain astronomy, monitoring stars primarily over different time scales. And it is a spectroscopic mission, again, near UV and visible light, and it has a relatively low spectral resolution. So you're basically looking at the broad shape of the spectra of primarily stars, and that's mainly what Mauve will be observing is stars. And it has a two mirror grating spectrograph, and the light is collected on a CMOS linear array detector. So as was said, it was launched late last year, November 28th, by SpaceX on a Falcon spacecraft, and it was, one of many things that hitched a ride on this particular launch to get up there. But it is operating, and I'll show you the first light spectrum in a moment. But to give you an idea of the sensitivity, so we have here a couple of different plots showing as a function of visible magnitude, the signal to noise that you get in a spectrum for different spectral types of stars, going from O-type stars all the way to M-type stars. And because M-type stars, most of their light is coming out and so these are at a couple of representative wavelengths. So this is 250 nanometers. So this is in the near ultraviolet. Yes?
The spacecraft, I couldn't see jets. I did not see a big coil for a magnitude talking. How do you keep the ACS?
So I'm not the engineer that designed that, but this is the spacecraft itself. This is the telescope detector instrument. This is the solar array on top. So there are some expendable gases on there that can be jettisoned to torque it around in many ways. But one thing that you will see is since it's small, it has a limited capacity for fuel of that sort. And so the field of regard in terms of where targets are accessible is limited to fairly equatorial. So because the further you go from the equatorial plane, you are using more and more of your fuel to point the spacecraft. And so just to conserve things, the general pointing of targets is only going to be relatively close to the equator. And you'll see, relatively speaking. M stars, the coolest stars, among the coolest stars in the galaxy, most of their light comes out at very, very red wavelengths. And so here you are in the near ultraviolet. And even a fourth magnitude star at visible wavelength, by the time you get to a near ultraviolet wavelength, is just not very bright. And so you're not getting much signal, and therefore you're not getting much signal to noise in a representative 100-second exposure of the instrument. But if you're out here at, 500 nanometers, so you're well into the optical, basically all those different spectral types are giving you roughly the same signal to noise at that wavelength, because that's very near the visible, the V band. The center of the V band is about 550 nanometers. And so sort of by definition, these are all about the same brightness at the wavelength that you're talking about for this particular representation. Now these, I should say, these estimates are pre-launch estimates. So this is before all the commissioning has been done, before the on-orbit sensitivity of the telescope has actually been measured. So there are a few different science cases that are being executed as part of the Mauve mission. So there are studies of hot stars, again, studies of flaring activity, studies of binary stars, and studies of the host stars of exoplanets. And then in my particular area are Herbig AEB stars. And these, again, are very young stars that have recently formed, and they still have material around them out of which planets are in the process of forming. So the science team itself put forward 10 different science missions or science themes. And these are the specific ones of those themes that have been approved for year one of operation. All the science that is done by Mauve is approved by the larger science team, and it's approved 1 year at a time. Now, some of these themes were put forward with the idea that you would be able to do them over 3 years, but the science team can reevaluate things after every year to see if things are going the way we think they should, and if we want to continue in that vein or not. So here is the map on the sky of the year one candidate targets. And again, assuming that the on-orbit performance of the spacecraft is roughly what we estimated before launch, we should be able to do all these. You might say 287 individual targets is not that much for a whole year's observing, but again, the idea is that you're going to observe these targets multiple times to do this time domain sort of science. This is the distribution of spectral types that you see here of the different targets. And as I was saying before, they're generally concentrated towards the celestial equator, just because that makes it such that you don't have to use as much fuel to get to targets very far away from there. So I'll give you a little bit of an overview of some of the science themes before I talk a little bit more detail about the one I'm specifically involved in. And so, as was mentioned, the Mauve mission was conceived originally as a way to study flare stars. And so these types of observations is that you will sit and stare at the star for hours upon hours upon hours and try to detect stellar flares, which we believe are analogous to solar flares in that it's a release of magnetic energy stored in the outer part of the stellar corona, and the energy is released through a process called magnetic reconnection, and that energizes the plasma and heats it up. And so these are some of the target stars that are approved in the first year. And what you see here is a simulation that was done. Again, this is pre-launch simulation of what a flare on one of these stars might look like. So this is a particular star with its Henry Draper catalog number. It's an early K-type star, relatively bright, a little bit brighter than 4th magnitude. And what you see here is the full spectral range that Mauve covers from 200 nanometers to 700 nanometers. So from about here shortward is all of the near ultraviolet light that you just can't see from the ground. And in blue, kind of at the bottom here, is what the star would look like when it's not flaring, when it's just sitting there. And then some calculations were done, simulations were done based on flares that had been observed on stars with, say, the Kepler satellite. And at the peak of the flare, you can see that it gets quite a bit brighter at multiple wavelengths, but in particular, it gets much brighter in the near ultraviolet than it does relative to the quiescence than it does at more optical wavelengths. And even during the weaker parts of the flare, it's still more visibly brighter in the ultraviolet than it is relative to the optical. And that's one of the goals why we want to study things in the near ultraviolet. Now, if you are familiar with looking at stellar spectra, you might say, well, that doesn't really look like any kind of a spectrum from a star that I've ever seen. And part of that is a combination of the fact that this is a very low spectral resolution instrument. And this is the spectrum that you will see as recorded on the Mauve detector. So it has all of the efficiencies of the mirrors, the grating, the detector, included in the simulation. So that's not necessarily the spectrum that the star itself is emitting. This is, in fact, what we think the spectrum of one of these things might actually look like. So what you see here in black is the observed spectrum taken with a much higher resolution spectrograph, but taken from the ground, of a flare from the star AD Leo, which is another very famous flaring star. This observation from this 1985 great flare observation was taken at McDonald Observatory. So this is a spectrum taken at West Texas. And what you see, all of these emission lines are the lines from hydrogen, the Balmer lines of hydrogen. This is H gamma, H delta, and going up to higher and higher members of the series until eventually it merges into just a flare continuum. And so even if you had a spectrum that looked like this, once you convolve it with the instrument response function, and particularly the spectral resolution of the instrument, it becomes and looks something like this. So that's what you're seeing there. But you're still able to see, certain wavelengths of light getting brighter than others. And that's one of the goals of the flare studies, is because while this particular observation here is one of the most powerful stellar flares that we've ever observed, clearly shows these individual lines of hydrogen and this what we call a Balmer jump, so that you see an increase on the short side of the Balmer line limit compared to the long side. Some flares from stars look like it could be a pure thermal emission, what we call a black body spectrum. And so a question, but a lot of those observations that look like it could be pure thermal are just taken with photometry, where you're taking you're measuring the brightness of the star in, say, the U band, the B band, the V band. You're not getting spectra. And shown here, you can kind of see it, is what the spectrum would look like. So this is a simulation with Mauve data, where you take basically this previous spectrum, you take one of the flaring spectra, you subtract off what the star looked like before it started flaring, and you can ask, well, what would be the difference between whether or not you had a pure black body addition to the spectrum, or you had something that had this very bright Balmer jump at the short wavelengths. And so even though you can't individually see the spectral lines, you can still tell what the emission mechanism is during the flare. And that's one of the goals of this particular science theme. Another goal is to look for evidence of coronal mass ejections. So I'm borrowing a video here from NASA that talks about the difference between a stellar flare or a solar flare and a solar coronal mass ejection. They can often occur at the same time. They are almost certainly related to each other. They're both related to the sun's magnetic field. But what we classify as a solar flare is something happening basically right at the surface of the sun. It is probably initiated up in the corona, but everything that you see is really coming from the very close solar surface. Whereas a coronal mass ejection is material being flung off into space. So this would be a solar flare. That's a coronal mass ejection, where you're just throwing material out into space. And these coronal mass ejections and flares are particularly important for the near-Earth environment because they interact with the Earth's magnetic field. They energize the aurora. They create the auroras on the Earth. But they can also create, that's an example of what we call space weather, but they can also disrupt satellite communications. They can do things to the Earth that are maybe not so desirable. For planets around newly formed stars, and particularly around very low mass stars, both solar flares, or both flares and coronal mass ejections are expected to erode the atmospheres, the potential atmospheres of planets around other stars. And so having a better understanding of how frequently they happen around different types of stars and different ages of stars is something that we would really like to know. Turns out coronal mass ejections, though, are very hard to detect on other stars. And in fact, there are not really any smoking gun observations that say, yes, we have seen a coronal mass ejection on another star. But one thing that we do see on the sun is some of those satellite pictures that you saw of the sun, which were where you could see just a few bright regions and a few loops, but the sun's surface was kind of dark in the background. What you were looking at there was light that's coming from particular atoms in the outer atmosphere of the sun at wavelengths that are typically in the ultraviolet or even in the X-ray part of the spectrum. And so this is showing the time behavior of one of those types of emission lines coming from the element helium. It's an ionized helium line. It turns out to be at 30 nanometers, so it's way off into the ultraviolet, far ultraviolet, near X-ray part of the spectrum. But what you see is initially it brightens because of the flare, but as a coronal mass ejection is launched into space, in this particular case, it was launched into space such that material was being flung in the direction of the Solar Dynamics Observatory, the SDO, which is the satellite that was taking these observations. And the material that it flung off actually started to absorb light from the flare itself on the surface of the sun. So initially it got brighter, but then it got fainter, and it got fainter than it was before the whole flare began. So it was material that was being flung off was absorbing light coming from the sun. And then as it continued to travel and dissipate and thin out, it got back brighter again and eventually tailed off over a long period of time. Well, the same thing that happens for this helium line should also happen for these Balmer emission lines, because the material that is primarily being thrown off is hydrogen. And while Mauve doesn't have the spectral resolution to see the lines nearly as sharply as you see here, it broadens them out a fair bit, but you should still be able to see a dimming of the spectrum at certain wavelengths that is indicative of one of these coronal mass ejections. So the hope is that Mauve, by having very good, excellent time resolution, but also having some spectral resolution, will actually will allow us to see these coronal mass ejections where we just really haven't been able to clearly see them before on other stars. Yeah.
What is the wavelength at which you're observing that?
This particular one here? So this particular one was observed at 30 nanometers. So that's not in the Mauve bandpass at all. This was from a solar satellite that has been on orbit for a while, the Solar Dynamics Observatory. That particular satellite doesn't have a spectrograph operating in the optical, so it couldn't get optical measurements of that. But the same type of phenomena have been seen from ground-based optical telescopes on the sun. So these are in UT hours. So this is the start of the flare normalized to 0. So this is 4 hours later, right? So this is roughly 30 minutes. And this is an hour later, 2 hours later, 3 hours later. So the coronal mass ejections are big, and it takes a little while for them to get moving out. So another thing Mauve is going to do is investigate the host stars of known exoplanetary systems, with an eye towards understanding what types of exoplanets or what types of systems that are out there might be habitable. One of the issues is um, probably everyone is familiar with the general idea of the habitable zone, but the habitable zone is the Goldilocks zone. It's where things are not too hot or not too cold, such that liquid water can exist on the surface of a rocky Earth-like planet. And the idea is if you're too close, here's for a sun-like star, if you're too close, it's too hot and the water can't be in the liquid form. If you're too far away, it's too cold, it freezes out. So there's a certain distance around a star at which the temperature is just right. And if you get to a hotter star, that distance moves out. If you get to a colder star, that distance moves in. These colder stars, most of the stars in the galaxy are these colder stars. The lower mass stars are much more plentiful even than stars like the sun. And so the habitable zones for around those stars happen to be much, much closer to those stars. But if you go back to what we were just talking about in terms of coronal mass ejections, that means that any planets that are in the habitable zone around these stars are more likely to be hit by coronal mass ejections if they do exist. And they're more likely to get a higher flux of ultraviolet radiation from those flares that might be happening on those other stars. And so there are concerns about, well, we don't need to just know the equilibrium temperature, and the equilibrium temperature just depends on the total luminosity of the star, how much total energy is coming out of the star every second. Most of that energy, particularly for the sun, is coming out in visible wavelengths. The amount that's coming out in ultraviolet wavelengths is a smaller fraction, but that smaller fraction is still very significant for things like atmospheric chemistry, for producing, for damaging maybe DNA and causing mutations and stuff like that. So having the handle on the ultraviolet habitable zone is particularly, or the ultraviolet radiation is important. And there have been a lot of studies, for example, using the Hubble Space Telescope to take spectra of ultraviolet spectra of exoplanet host stars. We get optical spectra of those host stars and infrared spectra of those host stars from the ground, but they aren't linked up very well between what's happening in the ultraviolet and what's happening in the optical and the infrared. And because Mauve can observe all across those, it's actually can help make sure that the calibration between the ultraviolet data and the optical data and the infrared data is correct, so that we actually know very precisely what the spectra is that may be hitting these planets around these young stars. And it will monitor some of these exoplanet host stars to measure the flare rates and the CME rates on these objects to see if they may be impacting the planets there. Oh, and this is just showing example simulated spectra of a few different types of stars that are believed to host exoplanets. Just move on a little bit to the hot stars that Mo will be studying, something called the classical BE stars. The classical BE stars are believed to, well, they are known to have some disks of material around them, but those disks of material are pure hydrogen gas. And it's thought that they are happening because the stars are rotating so fast that they aren't spheres, but they're oblong-shaped things just due from the centrifugal force spinning around the gas. And so you're supposed to see this as sort of a flattened ball here as to what it might look like. This is showing in the background, and you can sort of see a spherical surface here is what a star would look like if it was basically not rotating. And if you crank the rotation up to a high amount, it bulges out in the equatorial region. But not only does it bulge out, the equatorial region gets cooler than the polar region of the star, basically because it's further from the core of the star where all the energy is being created, and the way the energy moves through the layers of the star results in the pole being hotter than the equatorial region. And if you rotate this thing fast enough and it gets elongated enough, you add on then the radiation pressure just coming from a generally hot star, and that can start to make material flow away from the equatorial regions. But it's still spinning very fast, so it doesn't just flow straight away. It goes out into a more disc-like shape that is gradually expanding from the star. That last part is the idea that's not well tested. And so if these classical BE stars are recognized by peculiarities in their spectrum, basically they have hydrogen emission lines similar to what the flare stars that we showed a moment ago have. But the shape of their spectrum should change because of this difference between the hotter pole and the cooler equator, such that these are all spectra, simulated spectra for Mauve, of the same type of star, just rotating at different speeds. And so if the rotation is very, very rapid, you get a difference between sort of the optical versus the very blue and ultraviolet part of the spectrum. And if the star is not rotating at all, there's a more equal balance between the two wavelengths. And so that's something that Mauve will be able to test. We're doing a survey of all the known classical BE stars that are bright enough for Mauve to see if they all look like they are rotating very rapidly. And that's one of the main things.
Sounds like
Yeah, hours. Yeah, full rotation. Yeah, much faster. Yeah. It is. You have to be able to see, it has to be like at 45 degrees. If it was purely pole on, you wouldn't be able to tell. If it was at 90 degrees, you'd be able to tell. But if it's purely pole on, you wouldn't really be able to tell. And then this is the general theme in which I'm involved with, studying Herbig AEB stars. Ultimately, we plan to observe a lot, and I'm going to describe that in more detail. But in the first commissioning phase of the instrument, there's basically 4 of these stars that we want to try and observe. And so let me just move on because I'm going to cover it in more detail. But I did want to show you this image, which is the first spectrum from the Mauve satellite. So we looked at Eta UMA, which is a B3 dwarf star, visual magnitude of about 2, so a really bright star. And this is the spectrum taken from a combination of ground-based and then Hubble up here. And this is the spectrum that it looks like through Mauve. So again, this has all of the instrument response, all the different limits of sensitivity built into that cause this, that take the spectrum that looks like this and make it wind up looking like this. But as long as we know that it really should look like this, and we know that it comes out looking like this, we can figure out, okay, what is the transformation that allows us to go backwards? And we can then apply that to observations of other stars to figure out sort of what the true spectrum is within reason. I mean, you can't really go any better than the result.
There's a big peak in the middle that's not on the other one, and
Yep, and that's because of the spectral resolution. You're taking, so for example, you take these very sharp peaks and they just get broadened way out. I'll show you an example of what that would look like for these Herbig stars, because it does come important to one of the things I want to talk about. So this is the consortium of institutions that are part of the Mauve mission. And some in the US, some in Europe, some in Asia as well. All right, so Her big AAB stars. Well, her big AAB stars are young stars. They are newly formed stars. So our general cartoon of star formation is you start with a large dark cloud in our galaxy. So like the pillars of creation would be one of these areas in our galaxy where stars are forming now. If it becomes dense enough and cold enough, it will collapse under its own gravitational pull. But because everything's spinning a little bit, not all of the material ends up collapsing all the way down to form a star. Some of it lands in a disk around the star. And that's just from conserving angular momentum is what produces that. Eventually, what we observe, and there's still an open question as to exactly why and how this gets going. But for every young star that we see that has a well-developed disk around it, that also has an outflow. And that outflow tends to be collimated along the polar regions. Eventually, you use up all of the cloud material that was collapsing. Either it all falls in or the outflow blows some of it away. So you get sort of a naked star and its disk and that outflow. Eventually, planets start to form. You clear out the disk and you're left with a planetary system. So that's our cartoon of how star and planet formation proceeds. And the Herbig AAB stars are basically in this phase here. They've cleared out the material around them, but you still have a star and a disk. And they are just, I'll skip that for now. This is showing you pictures from the ALMA interferometer in Chile of disks around Herbig stars. And basically every Herbig AAB star has a disk. What you're actually looking at is emission from dust. When these disks form, it's mainly gas, but there's still, about 1% of the material is heavier elements that can form silicate grains, can form carbonate grains, can form ices, but it produces dust, and that dust is warmed up by the radiation from the central star, and it re-radiates at long wavelengths, millimeter wavelengths, which is where ALMA observes. And so ALMA sees these disk-like structures. Occasionally you see almost a solid disk, but more often you see disks with holes and rings and stuff like that. And those are probably telling us something about planet formation. The whole effort to understand how you produce these particular structures and exactly what their relationship to forming planets is a very active area of research. But that's not the story I'm here to tell you about today. This is what we think is happening around a newly formed star that has a disk around it. Again, you have the central star. If it has a strong magnetic field, that magnetic field probably truncates the inner part of the disk. The radiation from the central star heats up the material around it. The dust that is in these disks has a sublimation temperature of about 1500 Kelvin. So if it gets heated up by the radiation to hotter than about 1500 Kelvin, the dust will sublimate and it won't be dust anymore, it'll all be gas. And so inside of this sublimation radius, you get just gas. Outside of that sublimation radius, you get a mixture of gas and dust. And it is the dust in these regions that it was producing those images that we saw from the ALMA instrument here. If we zoom in a little bit more and think about only what is happening where the disk intersects the star's magnetic field, if the magnetic field is strong enough, it will basically capture all of the material at the inner edge of the disk. The disk won't be able to come all the way to the surface of the star, but the material is still being pulled in by the gravity of the star. It's just redirected to flow along these magnetic field lines. It falls onto the star, it accretes onto the star. When it falls onto the star, it's moving at close to the free fall speed, meaning that it's going a few hundred kilometers per second. When it hits the surface of the star, it heats up and produces a hot region near the surface of the star. Now, if the magnetic field is tilted a little bit, it doesn't produce these nice, idealized equatorial or rings of accretion zones around the equatorial regions. You might get just sort of individual spots because the disk material is grabbed on by particular parts of the field and accretes only onto certain parts of the star. And then as the whole thing rotates, you would expect there to be variability as those accretion zones come in and out of your field of view. So that's one of the things that we're looking to measure is the variability caused by this accretion. And depending on how strong the magnetic field is, if it's really strong, you truncate the disk really far from the star. If the magnetic field is weak, you truncate the disk closer to the star. If the magnetic field is almost non-existent, the disk comes all the way up to the surface of the star. So depending on exactly how strong the magnetic field is, exactly where these accretion flows hit the star can vary. Yeah, they're trapped to move along the magnetic field. They have to move along the magnetic field. Mm-hmm.
Difference is spin line of the
Disk in the star. Are you asking about why the magnetic field may be tilted relative to the spin axis? Well, what I can say is that when we do measurements of magnetic fields on other stars, we see in many cases they are tilted. Exactly why they're tilted, the whole idea of magnetic fields is an area of very active research because we don't understand them so well. I'm an observer, so I like to give my theorist friends a hard time. I'd basically say the magnetic field is the theoretician's Swiss Army knife. When they don't understand something, they say it's because of the magnetic field. But there's a lot about stellar magnetism that we just don't understand. Exactly what generates the magnetic fields, exactly why they behave the way they do. We see them, but truly understanding them, we're not there yet. Keeps me employed. So if the disk is truncated very far from the star, most of the material accretes near the pole. If the disk is truncated very close to the star, it might accrete closer to the equator, and if there's no field at all, it would accrete right at the equator. And so you would expect generally then if the fields are maybe not perfectly aligned, and you moved this in a little bit, this would be happening closer to the equator or further from the equator or maybe right at the equator. So depending on exactly where the accretion is occurring, you would expect more or less variability. So again, we're going to use Mauve to measure the variability. So what happens when you get accretion onto one of these young stars? Well, this model has been worked out from observations of much lower mass stars, not her big AAB stars, but we think the same general idea is happening. This would be for a colder star, roughly a K star instead of an A star or a B type star. You have light coming from the star itself. When the material falls onto the star and heats up, it produces extra emission that kind of looks like this. It has that kind of Balmer jump that we talked about. And then you add the emission from the accretion to the emission from the star, and you get a spectrum that maybe looks like this. This is an observed spectrum of a particular young accreting star. But so the basic thing to take away from this is, again, this is wavelength. This data is coming primarily from the Hubble Space Telescope. The accretion related emission is primarily coming out at ultraviolet wavelengths, right? So if you can look at ultraviolet wavelengths, you've got a leg up. Whereas if the disk comes all the way into the star, it is right at the equator, and it can heat up in a boundary layer, so you can get a hot boundary layer. But the only way that actually happens is if there is a difference in the spin velocity of the disk material and the star. If they're spinning at the same rate, now disks, we know, the closer you get to the star, you spin faster and faster. This is, it's basically Kepler's laws, it's orbital motion. It's, why Mercury has a short orbital period relative to the Earth, because it's closer to the sun. If you get even closer to the star, the orbital period is shorter and shorter. But as you accrete material onto the star, you're also accreting the angular momentum of that material. You're making the star spin faster. So if you get to a point where the star and the inner edge of the disk are basically spinning at the same speed, then you don't get this heated boundary layer, because the energy that produces the heating in the first place comes from the fact that you're taking a difference in the speed. You're taking kinetic energy of motion, slowing it down onto the star and turning it into heat. But if the speed of everything is the same, there's no heating. So I've already talked a little bit about that. Well, so what is some of the evidence that maybe the magnetospheres of these Herbig stars are different than other types of stars? Well, what you see here is some spectral lines of a helium atom in the infrared part of the spectrum, out around 1 micron. And what you see on the x-axis is in velocity space. Basically, you're just taking the wavelengths and using the Doppler shift formula to compute how fast the gas is moving. So positive velocities are blue shifted. That means material is falling in towards the star. And negative velocities are red shifted. That means material is being flung out away from the star. And so what you can ask yourself is, what is the maximum velocity that you see absorption on the red side? That's telling you the maximum speed that material is reaching as it's falling in towards the star. And so you can imagine, if you're falling in towards the star from a distance that's very, very close to the star, you're not going to speed up as much as you would if you were falling in from much further away, right? Gravity acts for longer, you fall faster when you hit the star. So what you see here are an analysis done for lower mass stars. The Herbig AEB stars, I didn't say, they are all 2, 3, 4 times the mass of the sun. They're more massive stars than the sun. We know of other young accreting stars that are called T-Tauri stars that are maybe 1 to a half the mass of the sun. So they're lower mass than the sun. So if you ask, what is the escape velocity from the surface of the star? The escape velocity is how fast you need to throw something away. It's the same speed as how fast would it be going if it fell in from infinity. So the escape velocity and the free fall velocity are the same thing, just one is going out, the other's coming in. So if you plot the speed at which you observe this fastest material versus the escape velocity, you see the low mass stars all kind of lie here, and the Herbig AEB stars lie here. And these numbers that you see, the 1.1, the 2, the 4, the 8, the infinity, that's what the escape velocity would be for falling in from a distance of 1.1 stellar radius, or 2 stellar radius, or 4 stellar radius, or 8 stellar radius, or from infinity. If you fell in from infinity, you would be going exactly the escape velocity, and you would be somewhere on this upper line. Well, so exactly why this guy's above the line, we won't deal with exactly, but the main point is that the Herbig stars are consistent with material falling in from much closer to their star than the lower mass stars are. And you can explain that if the magnetic fields on the Herbig stars are weaker or maybe not existent. Yeah. Because this is what's called a metastable line, which means that it has an upper state above ground state such that you can't get any transitions to the ground state. So you collect a lot of atoms in these upper states, and it just provides a way it provides greater visibility for what's going on than other spectral lines do, just because of the peculiarities of this particular spectral line. So we think that there's good evidence that the Herbig stars are different than the lower mass stars. And so we might expect different types of variability. So what might Mauve actually see? Well, so the Herbig A, B stars are hot stars. So they are A spectral type stars or B spectral type stars. This is what an A spectral type star looks like in the optical part of the spectrum going into the near ultraviolet. So each of these lines you see here are hydrogen lines from the Balmer series. If you heat up a region from accretion and imagine that it has a black body shape, it might look something like this dashed line. And this would be gas at about 10,000 degrees, which is a characteristic temperature for younger accreting, for lower mass accreting stars that we can measure things more clearly. That's a characteristic temperature of the accreting material. And so if you add this dashed line to the intrinsic spectrum of the star, the red line, you get the black line, or sorry, this sort of black dashed line up here. And the key is, well, okay, that looks a little bit different than the red thing that you started with, but it's a little hard to know, what's what. But the idea is if you renormalize this spectrum back to the original red spectrum, such that it looks the same at optical wavelengths, it's now brighter at ultraviolet wavelengths. So it's brighter than it should be, is basically the answer at ultraviolet wavelengths compared to optical wavelengths. So the fact that the ultraviolet part looks brighter than it should be relative to the optical part is what allows you to see that it's accreting in the first place. And so that's exactly what Mauve will allow us to do. It'll allow us to simultaneously measure the ultraviolet part and the optical part. So this is what it really looks like under the assumptions that we've given you. And this is getting ready to simulate that with the Mauve instrument. So again, this is a non-accreting version. This is a version that is accreting. But then once you take it through the Mauve instrument response, this is what it looks like. So you're talking about how you blur everything out. It doesn't really look the same. Well, you're right, it doesn't really look the same. But the two do look different from each other. And so that's what we should be able to see is the difference. And in particular, the difference is very small in the optical part of the spectrum, and it's very large in the ultraviolet part of the spectrum. And so again, it's seeing that relative difference between the two that will allow us to, one, tell if the stars are accreting, and then by measuring them over time, we will be able to see if the accretion is varying. What is the time scale it's varying on? And is it varying as much as we expect, depending on whether the emission is coming from the polar regions or the equatorial regions or exactly where? This is actually a simulation based on measurements that were taken of a particular young star that showed a very big accretion outburst and showed a dramatic increase in its flux. And so this is what Mauve would see in that case. But we were asking about the blurring effects. So in the gas that's accreting through this magnetic flow, at least for the lower mass stars, we know that it produces an emission in the hydrogen Balmer line, the H alpha line, which is at 65, 62 angstroms. And if you look at it with a relatively high spectral resolution, you see a very clear emission line compared to the rest of the spectrum. But if you take this and degrade it to the spectral resolution of Mauve, you get this red thing. Well, the red thing isn't nearly as dramatic as what you put in, but you can still see it. It's there as a distinct spectral feature. And so we will also be able to monitor that at the same time as we monitor the emission from the broader spectrum. This particular simulation that I put in didn't have that emission line in it, so you're not able to see it there. But what we do know is that when we look at these Herbig stars from the ground and we measure their H alpha lines, we see, so what you see here are two different stars, two examples of their spectrum with really bright H alpha lines. But on the bottom, what you see here is a measure of variability. This particular object is showing variability over a broad range of wavelengths, and the H alpha line is a little bit bigger than the rest, but not much. This star, again, shows a little bit of variability at a lot of wavelengths, but at the H alpha wavelength, it shows a lot more variability. And so again, that'll give us another handle on how these stars vary and what that might be telling us about the accretion process. And then the last thing I'll just say that Mauve will allow us to do is, this simulation I showed you assumed a pure black body spectrum for the extra thing that's coming from accretion. But we don't necessarily think that that's the way all stars accrete. In fact, what you see here these are all spectra of young stars, but low mass stars taken from the ground. And the red is the actual spectrum. The green is what the underlying star should look like, and the blue is the extra from accretion. So it shows this Balmer jump in the same way that the flare spectra that I showed earlier show the Balmer jump. And in exactly the same way that Mauve will be able to show us whether or not for stellar flares, whether you have a pure black body or something with a Balmer jump, Mauve should be able to show us the same sort of thing. And so with that, I will end. I'll be happy to answer any more questions, and hopefully maybe I can come back in a year or so and tell you what we actually learned from Mauve instead of what we hope to learn from Mauve. Thank you.
So for more questions, are there more questions in the room? Yep.
How do you pick your targets? Are there catalogs of these stars that you can examine?
Yes, there are catalogs, and what you see here are some of the targets. Well, these are all the targets for my particular study that we have selected for year one. Okay, and the difference between whether it's black or red is basically we want to stare at each one of these stars once a day, every day, for about 40 or 60 days, depending on the visibility of the particular star. But then for the ones in red, I want to, after we've done that initial stare for the 40 or 60 days, the ones in red, I want to come back every 4 days for the whole 3 years so that we can get the variability time scale for a much longer period of time. So the reason I picked these particular stars out of that catalog is they're bright. So again, Mauve is a small telescope. So this is the visual magnitude. The brightest one is about 4.5. The faintest one here is about 7.6. You know, the naked eye in a dark site, you can see down to about 6th magnitude. So these are not quite naked eye stars, but they're not 15th, 16th, 17th magnitude stars that you would need a much bigger telescope to look at. So that I picked the brightest available stars from the catalogs.
And maybe on that, do you have an expectation of the variability?
So if the variability, if the magnetic fields on these Herbig stars are basically non-existent or very, very weak, I expect the variability timescale to be very, very quick. but I expect the variability amplitude to be generally small. If the magnetic fields are large or strong, they truncate the disk at much further distances, and so the variability timescale, it would be on the order of weeks, but the amplitude could be very large.
Wow, that's exciting. Great, thanks. More questions? Yep.
Sure. I'm assuming you're very good at prediction, and that's why you got some of the time that was available for Mauve.
Yeah. I also paid some
But no
money.
matter how good you are, there's probably going to be some surprises on
Absolutely.
there that
Yeah.
may adjust your desire, we'll say, to have some of that finite time
Right.
available to it. I guess who makes the decision as to the priorities for the time that Mauve has available to it? Who would you make your case to as to you need an adjustment?
Yeah. So this is the group of institutions that are participating, and each one of them has representatives to the science team. And they basically all have an equal say, right? So there is a science team, and I'm on that science team, that we decide together, what's the best use of Mauve based on its performance and the science that we want to do. Now we're guaranteed some time. I mean, they can't all gang up on me and give me no time, right? But if my stars aren't doing what I thought they were going to do, and it's just really, really boring and nothing's happening, yeah, then they're going to say, well, maybe we should take some of the time from your project and put it into something that's being more productive. Now, we've already decided, though, that we're only going to schedule things for a year at a time. It's a 3-year mission. So, depending on how things go after the first year, we may completely do something different in years 2 and 3. And then also, of the total amount of time that's available, there has been some that's been held in reserve to follow up on new interesting things and to do some of that adjusting. So it's a dynamic decision-making process, and there's a committee that Rice has representation to, just like all these other places have representation to, that makes those decisions.
That's great. Anybody else here? Yep.
Oh, I was just going to ask, is the lifetime of the satellite?
So the
It's
nominal
pretty-
lifetime is 3 years.
3 years.
That's the planned lifetime.
Yeah.
And we're not going to service it. So
Yeah. This is a side question, but how do the flaring stars, they have to be a particular type of star, right?
they're generally
sequence.
K and M stars, so relatively low mass stars.
I see. And how do you detect that it is a flaring? Is that because the initial indication that it's flaring?
Well, so these all of those stars have been monitored from the ground using photometric measurements. So just looking at how bright is the star in the visual part of the spectrum, or the B band, which is the blue part of the spectrum. And for all of them, we have seen them get suddenly bright and then it tail off for a few hours. So we've seen all of these stars flare, but we just don't know what that flaring looks like at ultraviolet wavelengths. Now, for the exoplanet host stars, they are monitoring some of those flares. They are monitoring some of those stars for flares from the ground. But again, what is probably most significant for the atmospheres of planets around forming stars or forming planets around stars are those coronal mass ejections. And while we want to study stars, understand what kind of stars produce coronal mass ejections, we also want to study the particular exoplanet host stars to see, okay, how much are they actually flaring? Because not all stars flare at the same rate. So it's a combination of both sort of stellar astrophysics, what makes stars flare, and then what's happening on these particular stars because we know they have planets around them.
Right. Any more questions here in the room? Yep.
Great presentation. Everybody online loved it.
Good.
We did have one question. Will there be a paper on your findings available to the public?
So there will be. There is already a paper describing the instrument and the science team and what we are planning to do and what our motivation is. And once we start actually really collecting the data and analyze it, yes, we will be publishing papers. That hasn't happened yet. But it will happen. So like I said, in probably a year, the first scientific results will be coming out, and the papers will be out. And basically, all of the papers that are produced in astronomical research these days are all open access, so they are available on the web.
Fantastic. Thanks. More questions online? No, okay, great. Let me then be honest to present you with a small thank you. We really look forward to see you next year.
Sure,
The
sure.
results.
Yep.
Thank you so much.
Be happy to come up. Thank you so much.
Yes. Great. So maybe, yeah, we can switch over from this one. Yep. Just for the last slides of the day. Let me see. Zoom meeting and then share my screen. Great. So is it already up? Yeah. So that was it for today. So the next month's meeting will be well, first of all, we have the Novus meeting on May 7th. That's on a different date, so we moved that to next week when Chris is back. And then there will be the other Novus meeting per regular schedule the day before the main meeting on June 5th. So don't forget to connect with us through Discord, Facebook, email. We have YouTube, right? So a recording of today will also be eventually available on YouTube. And with all these clouds, there's a great radio astronomy talk there still. So you can build your own radio telescope and still do some observing, even though there are clouds. And of course, go through all the materials that we have there from the previous talk. So with that, it's already, the monitor here already dies. With that, thank you very much for this evening. And you have a great clear skies very soon. Thank you.